Welcome to this lecture series in linear algebra. In this lecture, we'll finally finish our discussion on permutations, and today's topic is sign of a permutation. So let's recall various things. First and foremost, we need to be familiar with the notion of the digraph of a permutation. I don't want to recall what this was. You can go back to earlier lectures to recall if you really need. Then we talked about cycles. So a cycle or a K cycle, where K is at least 2, is a permutation on a set X such that the digraph of sigma witnesses exactly one non-trivial cycle and that cycle has length K. So the word cycle has been used in two different capacities. One refers to a permutation, the other refers to a graph theoretic notion. Alright, we also saw cycle decomposition, that every permutation can be written as the composite of cycles, in fact disjoint cycles, except in the trivial case where your permutation is either the identity or itself is a cycle. Alright, so that's cycle decomposition, and then we defined what are transpositions. Transpositions are just two cycles of length 2 in the permutation, in the digraph. So let me repeat. A transposition is just a 2 cycle, and we just defined what is a K cycle. So a 2 cycle or a transposition is a permutation whose digraph witnesses exactly one non-trivial cycle, and that cycle has length 2. So that's a transposition, and we noticed that every permutation on a finite set can be written as the composite of suitable transpositions. Now these may not be disjoint, but every permutation admits such a decomposition simply because every permutation first admits a cycle decomposition, and then you can show that every cycle admits a transposition. I shouldn't say transposition decomposition, but every cycle can be written as the composition of transpositions. Combining those two facts shows that every permutation can be expressed as the composition of various transpositions. Alright. So one of our goals today is the following theorem, which will motivate the discussion that we are going to have. Fix any finite set, and suppose we have some number of transpositions with us. And suppose it so happens that their composite turns out to be the identity permutation. Then necessarily M is even. So this is saying in particular or equivalently that an odd number of transpositions cannot be composed in whatsoever way to give you the identity permutation. That's super interesting. And one of our goals is this particular theorem. In fact, we'll prove something even more incisive than this. And with that, let us now proceed. In fact, I encourage you to think about this before you look at what we are going to do. Think about this experiment, play around with various examples to maybe try to prove this yourself. It's a very, very interesting puzzle. All right. Okay. So what we are going to do is define the sign of a permutation, which will serve as an quote-unquote invariant. We will see. So here I have an example, but we will define things in general and understand whatever we define in terms of this example. So fix a finite set and fix a permutation on it. Then we write eta sigma, and this is not some standard notation or anything. So we define eta sigma as the number of cycles in the digraph of sigma, and here we also include 1 cycles. Now what do I mean by 1 cycles? So a 1 cycle is just a fixed point. For instance, in this example, the point 9 is not going anywhere under sigma. Sigma fixes it. So there is this loop present here which we just do not draw because it clutters things. So these are 1 cycles. We never defined it previously, I guess, in any previous lecture, but now we are doing it. Okay, so what is eta sigma in the example that we have above? Well, there is 1 blue cycle, 1 red cycle, 1 orange cycle, and 2 1 cycles. So it's a total of 5. Right? 1 plus 1 plus 1 plus 1 plus 1. So there are 5 cycles in the digraph of sigma. Then we define delta sigma as the size of the set X minus eta sigma. Right? It's some kind of deficit, if you will. That's why I've chosen this notation, difference or deficit, whichever you like. So what is delta sigma here? Well, it's just 12 minus 5, because size of X is 12, which is 7. So now finally we define what is the sign of sigma. The sign of sigma is defined as minus 1 to the power delta sigma. Okay, and therefore the sign of this permutation is minus 1 to the power 7, which is minus 1. So there are these concepts that we have defined. I mean, ultimately we just are interested in the sign, and it is unclear as to why we have defined it yet, but keep the previous proposition in mind. That is what is motivating these definitions. Anyway, what I'm trying to say is, given such a proposition, usually a way to prove such a thing is to associate an invariant with a permutation, or with the given object in our question. It's a transposition. So those invariants help you solve the problem, and that is the kind of thing we are trying to do. It is admittedly unclear at this point as to what good is this notion. Some arbitrary thing associated to a permutation. What good is it? We will see it is very good. So just let us make a note that if tau is a transposition, then what is the sign of tau? Sign of tau is minus 1. Why? Because suppose it is a transposition on a set of size n. Then how many cycles are there in the digraph of tau? Well, there is this 1, 2 cycle, and then remaining n minus 2 vertices each contribute one cycle. So the number of cycles is 1 plus n minus 2, because so the size of X is, let's say, n, then delta sigma is mod X minus the total number of cycles, which we are writing as eta sigma. So let me write that again. Mod X is n, delta tau, we are using the notation tau. Delta tau is mod X minus eta tau, which is n minus what? Well, there is 1, 2 cycle, so we get a 1 here, plus n minus 2 other vertices which contribute 1 to each one cycle. I mean, each of them lie on a 1 cycle, and there are n minus 2 of them. So we get an n minus 2 here, and therefore this number is 1, and therefore the sign of tau is minus 1 to the power 1, which is minus 1. So the sign of any transposition is minus 1. Okay, hopefully you understood this, and now let us proceed. So we will make some computations to motivate the main observation that will help us with our goal of this lecture. So this is the first set of crucial observations. We'll make 2 of them. They are cousins. So we have this permutation whose digraph I have drawn, and we are composing that by this transposition. So there is this red cycle, there is this orange cycle, and this transposition is kind of acting as a bridge between them. Note that it connects one vertex of the red cycle to another vertex. Connects in, I'm using that word very loosely, I don't literally mean connect, but it is kind of going between the 2 cycles. So what happens if we compute this composite? Something very interesting will happen. So what is this composite? Let's see. So 1 goes to 2. Well, suppose we want to know what happens to 1. So 1 is sent to 2 by the first one, and then this 2 will be fed to the second one, but 2 is fixed. So 1 goes to 2. Similarly, 2 goes to 3. Make sure you follow. 3 goes to 4. Why? Because, well, 3 doesn't go to 4. 3 goes to 4 here, but then 4 is fed to the second one. 4 goes to 5. So as a result, under this composite, 3 goes to 5. Okay, very nice. Now what happens to 5? Let's follow 5. 5 is sent to 6, but 6 is fixed by the second one. So 5 goes to 6. And if you follow, 6 will go to 7, 7 will go to 8, 8 will go to 9, 9 will go to 10. But now something interesting will happen to 10. 10, we want to know what happens to it. So 10 goes to 5. 5 is fed to the second guy, but that is sent to 4. So 10 is sent to 4 under the composite. Alright, finally, what happens to 4? We have 4. We see what it goes to 1, and 1 is fixed by the second one. So the answer is 1. So something remarkable has happened. These were two disjoint cycles originally, but after composing with this transposition tau, we get one big cycle. It is containing all the vertices that there were. Okay, so let's see what happens to the sign under this morphing. This permutation originally had a sign. Then we composed it by some transposition, this particular one, and we obtain another permutation. And let's just find out what are the signs of the two. So the sign of the first one, first let's see what is the delta of this guy. The delta is there are 10 vertices minus 2 different cycles. There is no one cycle, and there are two non-trivial cycles, one red, one orange. So 10 minus 2, which is 8, and hence the sign of this guy is 1. Okay, what about the sign of that guy? There are 10 vertices, but there is only one cycle, one giant green cycle, which is 9, and hence the sign of this guy is minus 1. So we see originally we had the sign 1, but after composing with this particular transposition, we get a sign minus 1. But the bigger message that you should carry with you is that if you have two disjoint cycles, there could be many disjoint cycles, but let's say there is a transposition that you are composing your permutation by, where the transposition has this nature that it connects two disjoint cycles, connects in this loose way I'm talking. So there may have been multiple cycles here. After this composite, you would see that these two cycles kind of merge into one big cycle, and the rest will remain as they were. So experiment around and you will understand what I'm saying. Make your own examples and experiment around. So that's very nice. What happened if we had composed in the other order? This is sent here and that is sent here. So basically this will be acting first and then this will be acting. So let's compute this composite. Okay, so 1 is fixed, but then 1 is going to 2, and 2 is fixed, 2 is going to 3, and so on. So let's see. 1 goes to 2 under the composite. 2 goes to 3. What about 3? Well, 3 is also going to 4. So 3 is fixed here, but then 3 goes to 4. So 3 goes to 4. But 4 is an interesting one. 4 goes to 5 under the first one. 5 goes to 6 under the second one. So 4 goes to 6. Now the story for 6 is the previous, just doesn't, 6 is invariant under the first one and 6 moves to 7. So what you'll get is 6 going to 7, 7 going to 8, 8 going to 9, 9 to 10. But what about 10? Well, 10 also goes to 5, just check. But 5 is interesting because 5 goes to 4 under the first one, 4 goes to 1. So what we will get is this big cycle. So note that the results of this composite and that composite are different. This permutation is different from that permutation, but in certain sense it is the same. In this crude sense it is the same, that in the first operation you got a giant big cycle, and same in the second operation. Those two cycles are different, but they are the same length cycles. Anyway, so let's compute the signs. So the sign of the previous one we computed earlier, this sign is, sign of sigma, the sign of this permutation. I didn't mean to say sign of delta. So the sign was 1, and the sign of this guy is, as it were, 10 minus 1, because there is one big cycle and 10 vertices. So the sign is minus 1. Okay. All right. So this is one set of observations, that if you have a transposition going across two disjoint cycles, and then you compose, you get one big cycle. It kind of connects the two cycles into a big cycle. All right. Now, some other kind of situation where we have one big cycle, and this transposition that we are composing by has one vertex at the cycle and the other vertex at a fixed point. So this guy is fixed point under the previous proposition. Under the previous permutation. So what happens to it? Okay, so let's compute. Starting with 1. Let me quickly just do the easy ones. 1 goes to 2, 2 to 3, 3 to 4. 6, what happens to 6? Well, 6 goes to 7 under the first one, but 7 goes to 8. So 6 goes to 8. 8 remains fixed here, but 8 goes to 7. And what happens to 7? 7 goes to 1, and 1 is fixed, so 7 goes to 1. So it's same kind of result that we saw previously. And in some sense it is the same result, because these two can be thought of as disjoint cycles, where this is a one cycle. So if you have a transposition connecting the two, the resultant is one giant big cycle. So let's see what happens to the signs. The sign of this one, first the delta of this one is 8 minus 2, because 8 is the total number of things in your set, and there is this one blue cycle and one cycle, so there are a total of 2 cycles. 8 minus 2, which is 6, and hence the sign is 1. But what is the sign here? Well, the deficit here is 8 minus 1. There is only one big cycle, no other cycles are there, and the sign is therefore minus 1. So again, after you compose by a transposition, you see that the sign flips, right? The sign was 1, but it has flipped to minus 1. What about this? So here also, very interestingly, you get the same result as the previous one. Even though we are composing in the reverse order, what you get here is the same as the previous one. So the sign flips again, right? Whatever is the sign of this one, this has sign 1, and as we saw, the sign of this is minus 1. So even now, the composite by a transposition seems to be flipping the sign. That property that we observed previously is holding on. Okay, what about this other situation where you have a cycle, but the transposition connects two vertices within the cycle, connecting 7 and 3, which are both on the same cycle? What happens then? So let's compute. This is even more interesting than the previous ones. So 1 goes to 2. What happens to 2? 2 goes to 3 here, but 3 goes to 7. 2 goes to 3, but 3 goes to 7. So 2 goes to 7. What about 7? 7 goes to 1, and 1 is fixed. So 7 goes to 1. So we have a shorter cycle now in the composite. In the previous example, we were getting bigger cycles in the composite, but now we have a shorter cycle. What about 3? 3 goes to 4. 4 is fixed. So let me draw a few edges and let you verify. Okay. And what about 6 now? 6 goes to 7, but 7 goes to 3. So 6 goes to 3. So very interestingly, this big cycle has been kind of broken down into two smaller cycles by our transposition, by this action of this transposition. So let's compute the signs. The sign here, or the delta here is, there are 7 vertices and only one cycle. So this is 6. So the sign is 1. While the delta here is 7 vertices but 2 cycles, which is 5. So the sign is minus 1. Again, the sign is getting flipped by the action of this transposition. But again, now we can compose in the reverse order and see what happens. Well, we get something which is different from the above, but in some sense, in a crude sense, it is the same kind of situation, because the result is as I'm sketching it. You can verify. So this is the composite, and again, the sign here is cos 1 and here minus 1. So sign is still getting flipped. So no matter what you do, you will see that the sign is still getting flipped. One situation that I haven't taken as an example is, suppose we had some permutation here, and the transposition here was not connecting any two non-trivial cycles, meaning suppose there were some few more points here which were fixed by the first one, and the transposition was messing around with those fixed points. That situation I haven't taken as an example, but you can take as an example for yourself and see what happens. Nothing very interesting will happen. The sign will still get flipped. So with all of this, all of these examples, you should be able to believe and prove that if we have any finite set and sigma is a permutation on it and tau is an arbitrary transposition, then the sign after you compose by the transposition on either side, wherever you want, either on the left side or the right side, you get that the sign of the composite is flipped. So you get -1 times the sign of the previous thing. So this is what we have seen in the previous examples, but you can easily convert those examples into a proof. By now you should have enough maturity to be able to write a formal proof using just those examples. Okay, so very interesting result has been proven, and as a corollary, suppose X is a finite set, and we have some bunch of transpositions, let's say K transpositions. We are not insisting that they are distinct or anything, they are just K transpositions on the set X. Then the sign of their composite, in whichever order you want, I mean these are arbitrary, so whichever order you compose K transpositions, you get that the sign is -1 to the power K. Okay, why is that? The proof is very simple. The proof is just that, suppose I want to show it for K equals 2. So this is -1 times sine of tau 2. Why? Because just think of tau 2 as sigma in the previous proposition. So I'm just using this equation. We have that, but we already observed that, yeah, so why did I write a -1? I wrote a -1 because of that. But I already know the sign of any transposition. The sign of any transposition is -1. We noticed that. -1 into -1, which is 1. And that agrees with the proposition, because when K is 2, this is a 1. So this holds. This indeed holds. And you can just argue by induction, or I'm sure you immediately see that this equation is true. And this shows, this proves what we wanted to, what we stated as a theorem in the beginning, that if you had an odd number of transpositions and you compose them, then you cannot get the identity permutation, because the composition of an odd number of transposition will have sign -1, while the sign of the identity permutation is 1. So this is something that we should have maybe commented on, but it's very easy to see that the sign of the identity permutation is 1, because what is the delta for the identity permutation? The delta is, well, let's say the size of the set is n on which the identity permutation is being considered. So n minus how many one cycles? Well, every vertex lies on one cycle. So n minus n, which is 0. And therefore the sign of identity is -1. Is 1. -1 to the 0 is 1. So therefore, if we had an odd number of transpositions, the sign of their composite would be -1, while the sign of the identity is 1, and therefore we can never have the equality. We can never have a composite of an odd number of transpositions as the identity. Alright, but more importantly, the following is a refined version. If we have a finite set and we have two permutations, then the sign of their composite is the product of their signs. Wonderful, wonderful result. And how do we prove it? The proof is very simple. If you use the fact that every permutation can be written as the composite of transpositions. So I'm not writing too much. All I'm saying is write sigma as a composite of transpositions. This can be done is what we have already seen in a previous lecture, and we recalled it in the beginning of this lecture. So each of these are transpositions. Maybe I'll mention that at least. So this and that are all transpositions. And same for this. So each theta I is a transposition. All right. So what is the sign of sigma? Sign of sigma, as we just saw in the previous corollary, that sine sigma is minus 1 to the power k, and sine theta is minus 1 to the power m. But sign of the composite, if you compose sigma and theta, it will be a composite of k transpositions and another set of m transpositions. So a total of k plus m transpositions. So the sign of sigma composed with theta is minus 1 to the k plus m. And that's it. If you take the product of the signs, you get the same thing as the sign of the composite, because the product of these two numbers is that number. So very nice. We have sign in the group theoretic language, sign function is a homomorphism, but we haven't discussed anything about groups. So this is in the best possible way we can state it. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.